Assalamualaikum. Good morning. So we continue heat of mixing and solution. We refer to elementary chemical process book, page 400 to 400 430. The heat of solution delta Hs is defined as the heat in enthalpy change as the change in enthalpy for a process in which 1 mole of a solute is dissolved in R mole of liquid solvent at the constant temperature. So as R become large, delta Hs approach a limiting value known as the heat of solution at infinite dilution. The heat of mixing has the same meaning as the heat of solution when the process involves mixing two fluids rather than dissolving a gas or solid in a liquid. As an illustration on how to use this data, suppose you wish to calculate delta H for a process in which 2 mole of potassium cyanide is dissolved in 400 mole of water. So first we calculate the mole of solvent per mole of solute. So solvent referred to the water, solid is the potassium cyanide. So 400 divided by 2. So we have 200 mole H2O in the solvent over mole of KCl. The value of delta H is in degree C R equal to 200 is listed as -3 kCl per mole. So it's mean that per mole of KCl that is dissolved. The total enthalpy is therefore delta H equal to N. This is specific heat of solution, or sorry, this is heat of solution. We get 6 kilocalorie. In table B11, refer to page 653, lists value of heat of solution for HCl gas form NaOH solid in water, and the heat of mixing at 205 degrees C of sulfuric acid liquid and water. Heat of solution such as those given in table B11 may be used to determine directly the specific enthalpy of solution at 25 degrees C relative to the pure solute and solvent at this temperature. Another common choice of reference condition, however, is the pure solvent and infinitely dilute solution at 25 degrees C. Another common choice of reference condition, however, is the pure solvent and infinitely dilute solution at 25 degrees C. Consider, for example, hydrochloric acid. This is table B11. A hydrochloric acid solution for which R equal to 10 moles water per mole of hydrochloric acid. So from table B11, the specific enthalpy of this solution relative to the pure hydrochloric acid and H2O liquid form at 25 degrees C is delta HS for R equal to 10. So R is the mole H2O per mole solvent, so mole solute is negative 69.49. Refer to the second column. Now the enthalpy of the solution relative to H2O liter vessel liquid and a highly dilute solution of HCl, let's say R equal to 1 million mole water per mole of HCl, very dilute solution, is the enthalpy change for the isothermal process. So we may evaluate this enthalpy change using any convenient reference state, in particular taking pure HCl gas and H2O liquid at 25 degrees C as reference in view of the latter choice. The specific enthalpy for 1 million mole of pure water equals 0, and the enthalpy change for the process is therefore apa ya, 5.65. You see, delta H equal to delta HS R equal to 10, which is 69.49 minus delta HS. This is talking about hydrochloric acid at infinite R equal to infinity. Value is 75.14, so overall delta H is 5.65 kilojoule per mole of HCl. Now is heat of solution. In general, the enthalpy of a solution containing R mole H2O per mole solute is for reference state of pure solute and solvent at 25 degrees C and 1 atm. So H specific enthalpy equal to delta H is R. And for reference state of pure solvent and infinitely dilute solution at 25 degrees C, so we have H specific enthalpy equal to delta HS minus delta HS at R equal to infinity. Note again that this enthalpy expressed per mole of solute, not per mole of solution. So solute refer to, if you refer to B11 is HCl and OH and H2SO4, limited to these three components. Okay. Exercise. The heat of solution of solute A in water at 25 degrees C is negative 40 kilojoule per mole. For R equal to 10 mole per H2O per mole A and negative 16 kilojoule per mole A. For infinite dilution, what is the specific enthalpy kilojoule per mole A of an aqueous solution of A? For which R equal to 10 mole H2O per mole A relative to pure H2O and A at 25 degrees C, that one is negative 40, yeah. Yeah. The other one is pure H2O and infinitely dilute solutions. Aqueous solution of A. The one is negative 40 minus negative 60, which is 20 kilojoule per mole A. So balance on dissolution and mixing processes. So the procedure. So when setting up an energy balance on a process that involves forming, concentrating, diluting a solution for which the heat of solution or mixing cannot be neglected, prepare an inlet-outlet enthalpy table considering the solution as a single substance. the pure component at 25 degrees C as reference state. To calculate the enthalpy of the solution at a temperature T is not equal to 25 degrees C, first calculate its enthalpy at 25 degrees C from tabulated heat of solution data that one refer to table B11, and then add the enthalpy change for the heating or cooling of the solution from 25 degrees C to T. The enthalpy change for the latter step should be calculated from tabulated solution heat capacity if they are available. If it's not available, you can refer to Perry Chemical Engineer Handbook, one is volume 2. Otherwise, use the average heat capacity determined from equation 8.3-13 for the heat capacity of the pure solvent for dilute solution. So 8.3-13 you may refer to page 419. It's for CP mixture. Example, hydrochloric acid produced by absorbing gaseous hydrogen chloride in water. Calculate the heat that must be transferred to or from an absorption unit if HCl gas form at 100 degrees C and H2O liquid at 25 degrees C are fed to produce 1000 kg per hour of 20 wet percent hydrochloric acid aqueous at 40 degrees C. So it is advisable to determine the molar amount of flow rate of the component of all feed and product solution before drawing and labeling the flowchart. In this case, 1000 kg per hour of 20% HCl aqueous. So from there, we calculate NHCl, which is the inlet for hydrogen chloride, that one in gaseous form. So we get 5480 mole HCl per hour. For, for water, it's 44,400 mole H2O liter, sorry, H2O liquid per hour. So both of this calculation is based on outlet for the HCl, hydrochloric acid, in aqueous form. Enthalpy table is shown below. This is the reference state. So the reference state here refer to the reference, is similar to reference state of table B11. So since 25 degrees C is the same as the inlet temperature for water in liquid form, so technically the enthalpy is 0. So you need to calculate H1 inlet for HCl, hydrogen chloride, and the hydrochloric acid. So calculate H1 and H2. So for H1, it's a CPDT based on table B2. You need to do some integration. HCl. Banyak HCl. Although it's liquid form. Yeah. So for table B2, remember there are A, B, C, and D. The value of A, if you taken it from this table, it's -3, meaning 29.13, in this case, times 10 to the power of -3. For the product solution R equal to 44,400 mole per mole water per 5480 mole HCl equal to 8.1. So refer to table B11, R equal to 8.1. So delta HA. So for the H2 calculation of H2, the pathway HA and HB. For HA is based on table B11 equal to negative 67.4. So you need to do interpolation between 5 and 10 for R. Then the heat capacity of aqueous hydrochloric solution are listed on Chemical Engineer Handbook as a function of the mole fraction of HCl in the solution, which in our problem is okay. So the calculation for HB here, especially CP for hydrochloric acid. Sit down. Yep. Oh, that's why. Sorry. So for table B2, the state for hydrochloric acid is gas form. Yeah, we call it hydrogen chloride in gas form. Although the formula is HCl the same. So in gas form, you can get from table B2, but in liquid form, uh, that's why it's referred to Chemical Engineer Handbook. So the first step in this calculation is to get the value of Cp. Once you get this value of Cp, then you can do the integration based on this Cp. So Hb here is at 26, so H2 is HA delta HA plus delta HB equal to negative 59. So Q equal to negative 3.35 times 10 to the power 5 kilojoule per hour. We'll try this exercise. So enthalpy concentration chart, single liquid phase. Energy balance calculation on liquid phase system involving mixture can be cumbersome when heat of mixing are significant. The calculation can be simplified for binary system by using enthalpy concentration chart. Upload of specific enthalpy versus mole fraction. We can refer to page 447, figure 8.5-1. It's a enthalpy versus mass fraction, the axis. And Hx chart for equation of sulfuric acid at several temperature. So this is specifically for H2O, sorry, H2SO4 sulfuric acid in liquid form. So it's a mixture of sulfuric acid and water in this case. That's why there are mass fraction of H2SO4 with 0. No, with 0 being the most the most diluted lah, meaning 0 amount of H2SO4, 100% amount of water. Meanwhile, for mass fraction 1, for H2SO4 is 100% of pure sulfuric acid. So we have here, this is the temperature. So the point on the isotherm of 8.5-1 were determined using the procedure outlined in the last section. Suppose, for example, you wish to calculate the specific enthalpy of a 40 wet percent sulfuric acid at 120 degree Fahrenheit. So if you know the heat of mixing of sulfuric acid at 77 degree Fahrenheit, the process 5 you would follow would be to bring pure liquid water from its reference temperature of 32 to 77. The sulfuric acid start at 77, 77 kat tengah ya. And so does not require this step. Mix the two liquid at 77 degrees C, bring the product solution to 120 and calculate them at the enthalpy changes for each of this step. So 1 pound mass solution, the negative, sorry, 0.4 pound mass H2O equal to 4.08 times 10 to the power of negative 3 pound mole. Then at 0.6 pound mole of H2O, liquid 32 degree Fahrenheit, 2.6 pound mole H2O, 77 degree Fahrenheit. That one we refer to delta H1. The heat capacity of liquid water is approximately 1 BTU per pound mass negative degree Fahrenheit. So 0.4 pound moles H2SO4 has sulfuric acid 77 degrees C plus 0.6 pound mole H2O 77 degree Fahrenheit to 1 pound mole H2SO4 solution equals 77 degree Fahrenheit. This one we consider as the delta H2. So we do the calculation. So delta HS referred to the table B11. Based on the table B11, delta H2 is equal to negative 279. The heat of mixing can be determined from the data to be negative 279 BTU per pound mole H2SO4. So for 1 pound mole H2SO4 solution equals 77 degree Fahrenheit to a pound mole H2SO4 solution equals 120 degree Fahrenheit. So this is we consider delta H3. The heat capacity of 40% sulfuric acid solution is roughly 0.67 BTU per pound mole degree Fahrenheit. So identify the delta H1, delta H2, delta H3 to get the enthalpy 40% H2SO4. 120 degree Fahrenheit is approximately negative 56 BTU per pound mole. So this 56 BTU per pound mole, this is the traditional method to calculate. So if you refer to table figures 8.5-1 at 0.4 mass fraction of H2SO4 or 40%, H2SO4 at 120 degrees C, the reading for enthalpy is 56 BTU per pound mole, which is similar to the normal method to calculate the enthalpy. So meaning it's accurate. Yeah. Next example 8.5-2 5 weight percent H2SO4 solution at 60 degree Fahrenheit is to be concentrated to 40 weight percent by evaporation of water. The concentrated solution and water vapor emerge from the evaporator at 180 degree Fahrenheit and 180 N. Calculate the rate at which heat must be transferred to the evaporator to process 1,000 pound mole per hour of the feed solution. So the block diagram is this. So the top product is for vapor, the bottom product is the liquid for evaporator. Okay. This is the mass balance. So reference state for energy balance is H2S, H2O liquid 32 degree Fahrenheit. H2SO4, so what does it mean? So this reference state is referred to reference state if you want to use figure 8.5-1, which is the enthalpy concentration chart for H2SO4 and H2O. So HF equal to 10 BTU per pound mass. This is for 5% H2SO4. This is reading from table, figure 8.5-1. The HL here also from the same table at 180 degree Fahrenheit. The enthalpy of water vapor at 180 degree Fahrenheit and A180 relative to liquid water at 2 degree Fahrenheit may be obtained from the steam table in Perry Chemical Engineer Handbook as delta HV equal to 1138 BTU per pound mass. Wait, let me see working table B5. Okay. So table B5 is for SI unit. SI unit tables B6. So all of it is using SI unit. So energy balance Q or the heat is equal to delta H enthalpy equal to M1HV plus M2HL minus 1,000 pound mole per hour of HF, which is equal to 984,000 BTU per hour. So having the enthalpy concentration chart, eliminate the need for all of the hypothetical heating, cooling, and isothermal mixing step that would normally be required to evaluate the total enthalpy change for the process. So this is the exercise. This exercise is based on enthalpy chart. H2SO4, H2O. Adiabatic cooling. The process involving adiabatic cooling, particularly adiabatic cooling. Hmm? Applicable simple to analyze. Adiabatic mixing, Adiabatic mixing when HX chart is available. Suppose XA is the mass fraction of A in a mixture of two species A and B, and that a mass M1 of solution 1 is mixed adiabatically with a mass M2 of solution 2. We will show that the condition of the product mixture x at 3 h3 is on a straight line on the hash x chart between the point corresponding to the fit stream condition. Okay. See, this is a XA1, XA2, XA3. So this is a adiabatic mixing. Mixing M1 with M2, you get M3. So this is the graph. The graph based on figure ni, based on the figure 8.5-D, the enthalpy chart. Yeah. So for adiabatic mixing XA3 is equal to M1 XY XA1 plus based on this equation. This is for adiabatic mixing. So, okay. Let's see the example. Example 3. Pure water at 60 degree Fahrenheit is mixed with 100 gram of an aqueous 80% H2SO4 solution also at 60 degree Fahrenheit. The mixing vessel is insulated well enough to be considered adiabatic. If 250 degree 50 gram H2O is mixed with the acid, what will the final solution temperature be? Second one is what is the maximum attainable solution temperature and how much water must be added to achieve it? Okay. So from solving question 8.5-3, the mass fraction of H2SO4 in the product solution is. So since this is adiabatic mixing, so you can use this equation. So that equation is the equation 8.5-3 is a M1 XA1 mass fraction of item. Okay, A1 here refer to H2SO4. Then 250 is the water. Divide by, okay. Okay. So H2SO4 that is how to say added into this solution is pure water. So if it's pure, because see here the pure water. So if it's pure water in terms of mass fraction of H2SO4 it's 0. So XP is equal to 0.23 gram H2SO4 per gram. So a straight line on figure 8.5-1 between point X equal to 0, T equal to 60 degree Fahrenheit. Di atas ya. 60 degree Fahrenheit refer to this value. And X equal to 0.8, 0.8 here. 6, wait. Wait. Goes through a point X equal to 0. 2, 3, T equal to 100 degree Fahrenheit. So kasih, yes. It intersect at 100 degree Fahrenheit. So the final solution is 100 degree Fahrenheit. Number 2, the line between x equal to 0. This is for second question. What is the maximum attainable solution temperature? And how much water must be added to achieve it? So the line between x equal to 0 T degree Fahrenheit, x equal to 0.8 T equal to 60 degree Fahrenheit pass through a temperature maximum roughly at x equal to 0.58 or 150 degree Fahrenheit. It's between 150, 140 and 160. So from equation 8.5-3, x 0.58. Okay, then we get the value for mass of water is 38 gram H2O to achieve that 150 degree Fahrenheit. Exercise. Okay. Oh, selamat. Use figure 8.5-1 to answer the following question. What is the specific enthalpy of 80 degree 80 weight percent H2SO4 equals 110 degree Fahrenheit relative to pure H2SO4 at 77 degree Fahrenheit and pure water at 32 degree Fahrenheit. So first question, so 0.8 at 110. So 110 is here. Then we have relative to pure H2SO4 at 77 degree Fahrenheit. 77 is here. And pure water at 32 degree Fahrenheit. Pure water here, 32 degree Fahrenheit. The last one, this is the 77. Oh ya, saya nampak. So the first question is the purple one. Yeah. So enthalpy wise, this is based on the reference state negative 97. For the second question, 100% the shape of the system on figure 8.5-1, I will get to read which a system must have the shape of 0 BTU per on mass. The answer should be temperature at 100% is here. For here it's 70, yang maknanya apa tu? Temperature. Oh, temperature. Oh, if it temperature is 77 because it's based on the based on the reference state. Huh? Okay. Another question is apa tu? Question apa tu? Question 3. Pure water at 32 degree Fahrenheit is, so pure water 32 degree Fahrenheit used to dilute 90% H2SO4 at aqueous 32 degree Fahrenheit. Estimate the maximum temperature of the product solution can achieve and the concentration of sulfuric acid in this solution. So the maximum temperature is, the highest can go is here between 180 to 200 degree Fahrenheit, which is approximately like 190. Here at this point, it's 0.65 or 65% H2SO4. I check for the number 4. So, thank you.